Imagine a chemical everywhere around you, in the ground, water bodies, and the air, yet impossible to break down. Known as and polyfluoroalkyl substances, PFAS are toxic forever chemicals that linger in the environment and in our bodies. Here, at the NUS Environmental Research Institute, we're driving impactful research, equipping researchers with the tools and support they need to detect, treat, and remove emerging contaminants in urban environments, one of which is PFAS.
My research group has been studying air quality in warm and humid urban environment. PFAS have emerged as a new and long-standing airborne pollutants everywhere around us. There's no regulation, there's no standard, even no methods to detect PFAS in the air. That's where my group's spending the effort, trying to understand PFAS in our urban airborne environment.
My research focuses on PFAS in the water environment, specifically their level of occurrence, their transformations in the environment, and how these chemicals bioaccumulate and biomagnify through the aquatic food chain. The challenge lies in detecting these chemicals at very low concentrations across various trophic levels and different phases. Ultimately, we want to better understand their risks to humans as well as ecosystem health.
Hi, my research group works on very carbon-dense ecosystems called peatlands in Southeast Asia, which are very vulnerable to forest fires. To put out these forest fires, flame retardants are used very frequently, and they carry a lot of these PFAS chemicals. These PFAS chemicals can get into the trophic levels, therefore in the entire ecosystem, also find their way to the food chain on which the communities dependent on these ecosystems will get exposed to. So we are studying the health of the community members as well as of the ecosystems on the effects of these PFAS.
My research focuses on novel water treatment technology to manage emerging contaminants, including PFAS and antibiotic resistance in water. And the challenges lies in the complexity of treating these pollutants at scale. But through our research, we have developed and are developing cost-effective solutions such as adsorption and advanced oxidation processes, membrane separation, and membrane bioreactor that can make a real impact on water safety by effective removal of emerging contaminants in water. But even so, some PFAS are difficult to detect at Hans level and are very resistant to breakdown. Therefore, further research is ongoing to overcome these challenges.
PFAS are notoriously hard to treat because the fluorine atoms provide a shield that reduces their reactivity, in particular to the hydroxyl radicals. So in my group, we use electrochemical processes in order to overcome that reactivity through a clever combination of electrodes. And that's how we are able to remove not only the parent molecule, but also eliminate the toxic byproducts. All this with very little energy consumption.
Whether it's detection, monitoring, or treatment, our researchers are supported with cutting-edge equipment, cross-disciplinary collaboration, and a shared commitment to protecting environmental and public health. At NERI, as we continue to advance PFAS research, we welcome industry partners and government agencies to work with us to co-develop innovative solutions and build a PFAS-safe environment.